Okay, I will continue now and finish this. Okay, we had problems with the power, and we had just started talking about courting imposed dormancy. This is the failure to germinate of seeds due to the restrictions of the seed coat, which we may call testa, pericarp, grooms, peria, lemma in cereals. For example, in Avena fatua, the coat or pericarp is responsible for court imposed dormancy. So this is the Avena fatua seed coat, which can prevent the entry of water and oxygen. This is Avena fatua seed. Again, here we are emphasizing the seed coat, which can prevent the entry of water and the oxygen, which are responsible for the germination process. Coming. Yeah, the lecture. Now, Acanthospermum hispidum seeds also have a coat which can prevent entry of water and oxygen. So what does coat imposed dormancy do? How do the seed coat structures prevent embryo germination? Number one, it can prevent water uptake. Number two, prevent gaseous exchange. Then it can contain inhibitors in the cover and inhibit germination process. It can prevent leaching of inhibitors from the seed, hence perpetuate dormancy. Modification of light reaching the embryo and blocking light penetration to the embryo. This can also interfere with the germination process. It can simply be a mechanical constraint which prevents the germination process. Now, seeds with seed coat imposed dormancy are sometimes called hard seeds. And we have got examples in these plant families: Leguminosae, Chenopodiaceae, Malvaceae, and Solanaceae. They exhibit seed coat imposed dormancy, which is associated with prevention of water entry into the seed. Still on coat imposed dormancy, you may find that the wax cuticle is the major impermeable barrier of water entry. These are polyphenols and lignifications which are outside the embryo. Some seed coats prevent gaseous exchange, such as seeds. Such seeds are said to be gas hard. Again, another example of the xanthium species. You'll find that some weed species have got various mechanisms which are responsible for their seed dormancy. Impermeability of oxygen may be due to the presence of mucilages in and around the seed coat, and or the consumption of oxygen by the seed coat itself. Still on coat imposed dormancy, we are looking at the mechanism. You have insufficient availability of oxygen to support levels of respiration which are required for germination or to oxidize inhibitors. Germination inhibitors are located in the embryo cotyledons and the endosperm or the seed coat. You can have some germination inhibitors which are found inside the seed, and the outer coverings may prevent leaching of these inhibitors. And of course, we are saying they may be actually present in the seed coat. So when the embryo is isolated and put in water, the germination inhibitor is leached out, and this can allow the germination process to take place. For example, in Avena fatua, wild oats, and the xanthium species. Now, there are some seeds which we call photoblastic seeds, which require light so that they can germinate. Now, these seeds have got a hormone known as the phytochrome, which exists in two forms. And it is the ratio of the two forms which determine dormancy. We have what we call the active phytochrome far red, PFR, and the inactive phytochrome red, the PR. The ratio of these two forms will determine whether the seed is going to be dormant or not. So the optimum ratio is established after exposure of the seed to white light, which converts PR to PFR in the embryo. So outer coverings form a filter to high incidence of light on the seed, and this can modify its effectiveness in covering, in converting PR to PFR. The example of the weed where light is involved is Canopodium album or Fetian, which has two types of seeds. Seeds with dark seed coats are less responsive to light, whereas the other seeds are responsive to light. Now, dark seeds will filter out light and reduce the conversion of PR to PFR when exposed to light. Hence, they remain dormant for longer periods. But if you look at these seeds, we have got those which are white. This can easily germinate. Now let us look at the dormancy which is genetically controlled. So innate dormancy may appear to be under simple genetic control, but sometimes the genetic control is modified by maternal effects. Now we've got this example, Nicandra physaloides, which has got some seeds differ in terms of isochromosomes. You have some seeds with 2n equals to 20. This can easily germinate. But those with the 2n equals to 19, they are dormant. So you have got isochromosomes which are shown here. This can influence dormancy. The genetic control of innate dormancy is also apparent in Spegula avensis seeds. Okay, let me. This weed can produce three types of seeds. You have a homozygous papilla form bearing a 120 papilla. Then you have got a homozygous smooth form and a heterozygous form with the 60 papilla. So there are three types. It is those with the papilla seeds which can germinate readily around 21 degrees Celsius. This is an example of genetic polymorphism, which is the production of seed of divergent morphology and behavior as a result of genetic segregation. So this is under genetic control. Somatic polymorphism and innate dormancy. Now what we call somatic polymorphism is production of seeds of different morphologies or behavior on different parts of the same plant, not as a result of genetics, but somatic differentiation. Again, we have got Xanthium species which can have two seeds which are produced on the single dispersal unit. One deeply dominant, the upper seed, one deeply dormant, which is the upper seed, and the other one which can easily germinate, which is the lower seed. So the dormancy breaking requirements of two seeds are different, and the result that at least 12 months normally separate the germination of the two seeds. So this is one of their survival mechanisms. Somatic polymorphism and innate dormancy. Now in a vinifatua, you've got the grains of different positions on the spikelet. You have different germination requirements. This polymorphism is important in spreading the germination of seed from the same plant over time. So polymorphism is widespread in the Compositae family, Cruciferaceae family, the Chenopodiaceae families. So this was innate dormancy, quite a long story. Induced dormancy is a very short story. This results as a sudden physiological change due to changes in temperature, moisture, and oxygen levels. Even when the conditions revert back to normal, dormancy persists after the environmental conditions have changed. Seeds buried by tillage may not germinate when brought to the soil surface. Enforced dormancy. This is due to placement of weed seeds deeper than probably 5 centimeters during tillage. It is caused by the absence of red light under the surface. So red light induces germination in seeds by activating phytochrome system attached to the protein molecule in the seeds. So far red light deactivates the system and thus induces dormancy in weeds. Dormancy does not persist when the environment changes. So this is enforced dormancy. It's temporary. Now let us wind up by looking at the environmental conditions that can terminate, that can cause or terminate weed seed dormancy. Light. Light causes weed seed dormancy. Some weed seeds require light in order to germinate. For example, Garden Soga parviflora, Portulaca oreaceae, Chenopodium arbum, and Amaranthus species. Breaking dormancy is related to light, which exists in two forms: promoting and inhibiting form. Now the promoting form is favored by red light and the inhibiting form by far red light. So let us look closely at the light effects. You have inside the seed, you have got inactive form of phytochrome. If you expose it to red light, you can promote germination. Then you have the active form, which is PFR. If you expose it to far red light, you inhibit germination. So leaf canopy can suppress germination where you have promotion of far red light, which inhibits weed seed germination. Immature embryo. Presence of immature embryo. Some weeds shed seeds with immature embryos. So seed storage is required for several weeks before you can get germination. We have talked about seed coat. Seed coats can be impermeable to water and oxygen. These are hard seeds. Amaranthus hybridus seeds can have hard seeds. In order to have germination, you will need to sclarify the seed coat or damage the seed coat in order to allow germination process. This can be achieved using acids or microbes. We know that hard seed coat may prevent germination. Radicle cannot actually penetrate it. So hard seed coats need to be scarified first by rubbing, probably using sandpaper or just using a pin to damage the seed coat. I mean, these are some of the things which we do when we want seed germination to occur. Now, with inhibitors, these are actually internal and they can stop germination. We may put the seeds in water to allow leaching of the inhibitors in order to improve seed germination. But there are some inhibitors which can act externally, like for example during aridopathy. Oxygen, if we have low oxygen environments, this can reduce seed germination. Temperature, we have got minimum temperature which can stop germination. Also maximum temperatures which can stop germination. And this can vary among weed species. Amaranthus species will remain dormant at 20 degrees Celsius or at room temperature for up to 6 years. So raising the temperature would break dormancy. The after ripening requirement, this is necessary for some weed seeds because this is related to the maturity of the embryo. Embryo is fully developed but will not germinate even if the environmental conditions are suitable. So, well, in this case, you can have a mature embryo, but because of certain conditions, it will not germinate. The seed, however, will germinate after it is ripened, after this period. Well, I just want to summarize this dormancy. Remember, we are starting with the seed, which has to germinate. And the dormancy, we can classify it as innate, induced, and enforced. So you start with seed dormancy. We have got primary, which is innate. Secondary, which you can split into two, which is induced or enforced. And under innate dormancy, whenever you are going to follow up the notes, remember that we are starting with embryo dormancy, which can be a number of things. We are dealing with number one, immature embryo, Acanthospermum hispidum or Xanthium strumarium. So it is only after the embryo has been matured that you can have germination. Or you can have the growth regulators, ethylene in a vena vatua, in various weed species, you have gibberellins, GA and ABA balance, which control germination. Remember, if you have more GA, you can break dormancy. If you reduce ABA, you can break dormancy. If you increase it, you actually cause dormancy. Other growth inhibitors, things like coumarin and the phenolics, these have to be taken out of the seed through leaching or putting your seeds in water so that they can germinate. We have got seed coat dormancy. What it does are those 6 things. It can be a barrier to water entry into the seed. It can prevent oxygen, or it can just restrict embryo growth. It may contain growth inhibitors, or it may prevent growth inhibitors from leaving the seed, or it can alter the red light and far red light ratios. There's this genetic polymorphism, the presence of isochromosomes in the seeds of Nicandra physalis, which are the causes of dormancy. Genes may control seed coat texture in Setaria avensis, where there are smooth, rough textured seed coats with the different requirements. Somatic polymorphism in Xanthium strumarium, you can have 2 types of seeds with the different dormancy characteristics. Avena fratura on different positions of the spikelet have different germination requirements. This brings us to induced dormancy, which is caused by environmental conditions. It could be cold conditions. Then enforced dormancy, it could be conditions which are not suitable for germination, for example, deeply buried seeds. But this is reversible easily. But the other one, induced, it's not easily reversible. How do we terminate dormancy? This is what we can do, to deal with the dormancy. Scarification, you damage the seed coat. Stratification, these are the low temperatures. You freeze the seeds for some time, then bring them to high temperatures. Temperature, you should know the requirements of seed germination requirements. The temperature which is suitable for seed germination, it can vary among these weed species. Use of gibberellic acid and the potassium nitrate. So this should be it. So use the summary first so that you can really zero in on the points which you want. This may help you to address certain issues. So this is it. This is the end of this lecture.